Okay, welcome back. We're now going to review several of the available methods that we have. And so imagine that for each individual in the study, we compute the estimated probability that y is equal to 1. So this is the logistic regression probability, and it's e to the logit over 1 plus e to the logit. So this is computed for each individual. Remember that once an individual is part of a covariate pattern, that every single person in that covariate pattern, no matter what their value of y is, every single person in that covariate pattern has the same estimated probability that y is equal to 1. So just by being in a bin, being in that covariate pattern, you share the estimated probability with everybody else, with your bin mate. Everybody else is in the bin with you. So given you have the estimated probabilities pi hat 1, pi hat 2 up to pi hat n, an informally used approach would be to rank order these n probabilities and establish deciles of risk. And we talked about that last week, where we took the probabilities. Remember, we had the women come back to our study site. They were given probability tags. We asked them to get in a big long line from lowest probability to highest probabilities. And the 10 women who had the lowest probabilities of having a low birth weight baby constituted the first decile of risk. And the next group, 10% of women who had the next smallest probabilities of having a low birth weight baby constituted the second decile of risk, and so on. The 10% of women who had the highest probability of having a low birth weight baby constituted the highest decile of risk. If n over 10 is not an integer, this is not a problem. I mean, clearly if there was exactly 200 women in the study, then each decile of risk would contain 20 women. Of course, not even exactly true, because if two women had the same covariate pattern, or even if they didn't, they had the same probability, you wouldn't put one woman whose probability is 14% in one decile, and another one whose probability is 14% in another decile. You'd probably keep those with the same probability together. So you still wouldn't have exactly the same number in each decile, and it doesn't matter. Also, we talk about deciles, but these deciles, yes, it can be 10% of the data, but the methods that we're talking about, if you have a very large data set, you don't have to restrict it to 10% of your data in each of the deciles. You can talk about having 20 groups. Or you can talk about having 50 groups. As long as you have enough people in each decile to get a reasonable estimate of the expected number to have the event, then in fact this method can work. But in general, we developed, the methods have been developed for having 10 groups. So the model is a good model, or that is the probabilities produced by the model are accurate representations of the true outcome experience in the data if those people who actually develop the outcome have relatively high probabilities of y equal 1, that is large values of pi hat, and those who don't develop the outcome have small values of pi hat. Now that's the way it should be, and again, having some individuals who depart from that is not necessarily a problem, because these are overall methods of goodness of fit. They're not looking at specific poorly fit covariate patterns. Now if you're interested in specific poorly fit covariate patterns, I would highly advise that you get a copy of our book. We spend a lot of time talking about diagnostic statistics, which is really focused on looking at the individual covariate patterns and looking to see how departures of individual covariate patterns, large values of the individual diagnostic statistics can affect overall model performance. But that's not what we're talking about today. We're talking about overall measures of goodness of fit. So the methods that have been proposed, the simplest method is that for each of the 10 deciles of risk, you look at the observed number of events in that decile. That is, you just take, for example, in the reunion of the women with low birth weight baby study, we said that let's suppose that we had 20 women in the first decile. If you sum up the y values among those 20 women, that's the observed number of low birth weight babies, because those who had a low birth weight baby had y equal 1, and those who did not have a low birth weight baby had y equal 0. if you sum up over all of the women in that decile, if you sum up the estimated probability of having a low birth weight baby, then you get the expected number in that decile. And we talked about the fact that hopefully the observed number of events in each decile corresponds very well to the expected number of events in that decile. And so you do this for all of the deciles, that is j equals 1 to 10, and d sub j denotes the decile, or the people who belong to that jth decile of risk. So you're going to do this, you're going to compute the observed number and the expected number in each of the 10 deciles of risk. And so now we consider these pairs, the observed number and the expected number, for each of the 10 deciles. And now one method that has been used, not very often, but people have used for lack of anything better, was simply to plot those observed and expected counts over the 10 deciles. Now, you can see that, you know, if you sort of didn't have this line here, and if you plotted the points, the observed and the expecteds, so you'd have 10 points plotted on this graph, you would hope that the points could be fit by a straight line going through the origin having slope of 1. I mean, you would hope that basically if the expected number of events in a decile was 10, that the observed number would be 10. Now let's say, for example, that when you plotted these 10 points, the points went along pretty well, and then they drifted away from this 45-degree line in a manner like this. Well, then you would see, or you would be able to say that, that basically the model was tending to produce probabilities that were too low, because the observed number of events were larger than the number of events that were estimated to have occurred by the model. And similarly, if you saw a drifting of points up here, then you would say that the model was overestimating the probabilities, because the probabilities that are being produced result in expected numbers that are greater than the observed numbers. So by looking at this again, if the points all fall on a 45-degree line, this is good, because this would suggest that the model is producing good values. And actually there are some new methods that are being developed that are looking at this kind of a drift of the counts, of the experience, away from what is expected by the model, and to make decisions about whether or not you have good fit. But the problem with this method is this is an eyeball method. I mean, this sort of, you look at it and there's no p-value associated with it. There's nothing, no lights that turn on and say, aha, this is a bad fit. You look at it and you sort of decide whether you think that the drift of the points about this 45-degree line is serious enough to think that the model doesn't fit. And I think I mentioned last week that I've had a student go through and look at every single copy, every single paper produced in the American Journal of Public Health, looking at the whether they did logistic regression in their study, and whether they had any attempt at evaluating the fit of the model. If they had done this would have suggested that they did something concerning the fit of the model. But most studies don't do that, or at least at that time, many studies made no attempt to look at goodness of fit, but this would have qualified as a reasonable method of goodness of fit. Now, so that brings us to the next method, and this is basically called the Pearson chi-square statistic. And often in statistical packages you will see the Pearson chi-square statistic presented as part of the output when you are looking to evaluate the fit of the model. So this is a good place for a break, so let's break here, and then when we come back we'll look in detail at what the Pearson chi-square statistic tells us.